Welcome to lecture 1.5. In this lecture, we're going to talk about transfer function representation of systems. This is a very important representation from the control systems perspective. So we'll start from where we left on the last turn. On the last turn, we took this RLC circuit up, a simple RLC circuit, and we were trying to find out, write down the differential equation governing the circuit from first principles. And we wrote down this differential equation that you see. So Vt is equal to Rit plus Ldi by dt plus 1 by C integral Id. Now, this is not really, although it represents the physics of the problem entirely, but it is not very useful from the control systems perspective as such directly. What we would like to have, as I've told you before, is something in the form where we're able to put it in this way, like you have an input going into the system, you have an output coming out from the system, and you have the system inside, right? I would like to have this block diagram representation for this differential equation. Now, assuming that the voltage is the input to this system. It's an electrical system which is responding, right, to certain inputs. So assuming that voltage to be the input and assuming current to be the output for this system, which is a circuit right now. Is there some way by which we can have this kind of a representation for it? The answer is yes, and we already know a little bit about that. We have done Laplace transformation in mathematics courses, and Laplace transformation is a very useful tool for creating block diagram representation of systems that we are trying to control. So this is the governing equation, and we are saying that this voltage is the input to the system, right? And the current is the output from the system, right? So if we apply Laplace transform on both sides to this equation, this is a differential equation, we'll get the Laplace transform of a function of time is a function of s, right? And r is a constant, so ris. For this, you know that this is the Laplace transform would be s times lis, and for the integral term, you divide it by s, so 1 by c is. Now we have written this assuming initial conditions to be 0. Assuming initial conditions are 0. Otherwise, you'll have to put initial conditions here and also here. So now, what this Laplace transformation does is actually converts a differential equation into an algebraic equation. Now, this is an algebraic equation in S, right? So we can try and simplify this and get Vs is equal to R plus Sl plus 1 by Sc, and we have this Is outside. And to get it in the input-output form, we can say that the output Is is equal to Vs divided by R plus Sl plus 1 by S, right? So if we look at this equation and we look at the representation that we were aiming at, it was that this V, which is now Vs, we are drawing the block diagram in the S domain. This V is entering into the block and I is coming out of the block, because V is the input and I is the output. And everything inside the block actually gets multiplied to what is getting in. So this is it. So Vs into 1 by R plus Sl plus 1 by Sc gives the IS. Basically, what you have done is actually you started with the schematic. This was your schematic. It was a circuit diagram which basically explains the scheme of operation, and then you drew a functional block diagram in your mind, right? So your functional block diagram was something like this. You said that there was an input going into the circuit, right? So you had a circuit here, an RLC circuit, and you had an output coming out from here. So you made this functional block diagram. We did not make it explicitly, but we made it in our mind functional block diagram. And then came the third phase, which is the modeling phase. And in the modeling phase, what did we do? We wrote down the basic equations from the governing physics, from the first principles. So the first principles give us this basic differential equation, which govern the the uh, the mathematics, which govern the physics of the circuit, right? And then we use these first principle equations, and we were able to write down what is this. This is actually the block diagram representation. We drew this block diagram in the S domain. It is not in the time domain. It is in the S domain. Uh, right? But nevertheless, we have a representation which is very convenient, right? So this representation a representation of some system dynamics in terms of functions of the frequency variable S has a special name. So we have written Is, which is the output, is equal to the input, which is the voltage in this case, divided by some number. So if you write down Is by Vs, we get what we put inside the block, this R plus SL plus 1 by SC. Now this ratio, output, right, divided by input, right, the Laplace transform of the output divided by the Laplace transform of the input, assuming all initial conditions to be zero, is called the transfer function, right? So this has a precise definition: Laplace transform of output divided by Laplace transform of input, assuming initial conditions to be zero, is called the transfer function. Right? So you can represent your transfer function by normally we represent it like this, by GS. So what you have done is actually you have represented your circuit like this by a simple block called GS. Now, what is the utility of doing this? The utility is that normally, in case you have a number of systems and subsystems interconnected, like we were talking about the self-driving car the other day, you will not have just a circuit. You'll have many circuits. You'll have motors. You'll have gears. You may have a number of other things depending upon the complexity of the model that you're trying to handle, right? So what is very easy is that it is very convenient to then actually connect the different blocks together like this, right? So one block might be your circuit, another might be this voltage or current might be going into the motor, right? Feeding the motor, and there might be other blocks. So you can actually make a block diagram very conveniently if you're able to represent every subsystem as a transfer function, right? So we'll try to do this for different systems, right? In this unit, We'll take electrical systems, then we'll take mechanical systems, right? We'll take electrical systems first, right? And try to find the transfer functions. Then we'll take mechanical systems, right? Mechanical systems. And then we'll combine the two. We'll talk about electromechanical systems, right? Only when we do electromechanical system modeling and we're able to draw a block diagram representation like this for the whole electromechanical system, can we actually draw the block diagram, understand the block diagram for the antenna azimuth position control system that we studied in the beginning, right? So it is a step-by-step process, uh, uh, which everybody amongst us has to follow, right? Now, coming back to this differential equation, what is special about this differential equation? Does every system have a differential equation like this, or is it peculiar in some way? So let me write this down again here. Right. So we see a little discussion about this is important. Is equal to RIT plus LDIT by dt plus 1 by C integral IT dt. Now this is what actually an integral differential equation, right? And you can write this as a pure differential equation if you write IT, which is basically equal to the derivative of your charge, right? So you can always, the QT is charge, right? Charge flowing through the circuit, right? So you can, if you put this thing inside this, you'll be able to write something like this: Vt is equal to R dqt by dt plus L. Now this will be the single differential of current, will be the double differential of charge, d square qt by dt square, plus the integral of current is the charge plus qt by c. Now why did I write this? I wanted to write the differential equation. I wanted to simplify this, right? Differential equation directly. Now this is not a general differential equation. If you remember from your maths course, this is an ordinary, right, differential equation, right? It also has constant coefficients, right? These coefficients are constant. These are called coefficients. It is also linear, right? It's an ordinary differential equation with constant coefficients, and it is non-homogeneous, right? What does this mean? When we say it is an ordinary differential equation, we want to basically separate it from partial differential equations, right? So it's an ordinary differential equation because it has only one independent variable, right? One independent variable. In this case, it is time. You're differentiating only with respect to time, right? If you had one more variable, say space, then you would have a differential equation, right? There's one more thing. It's an ordinary differential equation and it is in one variable, right? There's one variable in this. Now what does this one variable mean? You could have a differential equation in which you have a number of variables, right? So for example, dxt by dt plus d square yt by dt square plus so on and so forth. Here the variable which is the dependent variables which are being differentiated are more than one, right? So it has only one variable basically which we are differentiating. Now it has constant coefficients. I've already explained that. It is non-homogeneous. A differential equation is called non-homogeneous when it has a forcing function, when there is an input to the system for which you are writing the differential equation. So in this case, the forcing function is the voltage, right? So if you did not have a forcing function, right, if if this term was absent, right, that the term which is actually providing input to which the system is responding, then the differential equation would have been homogeneous. And why is it linear? It is linear because if if the response to say input x1, if the response to the input v1t, if the response is I1t, so this is the definition of linearity, and the response to v2t is I2t, then the response to the sum of the two, v1t plus v2t, would be I1t plus I2t. This is called the principle of superposition. This is one principle which is holding in this circuit. So if the response to the input v1t is I1t and the response to the input v2t is I2t, then the response to the sum of the two inputs is equal to the sum of the two outputs, right? This is the principle of superposition, and the another important principle that it is following is the principle of scaling. So if the response to v1t is I1t, then the response to some constant times v1t would be that constant times, right? That constant times I1t. So this is the principle of scaling. So these two principles it is obeying, that is why it's called linear, right? Okay. So ordinary differential equation, which is linear, has constant coefficients, right? These generally represent systems which are called linear time invariant systems. Right? This is very important. Linear time invariant systems. LTI. Right? So an LTI system would be the one which is linear, right? So the differential equation governing it is linear. It follows these two principles, and you can check whether these two principles are followed by putting them in this actual equation and trying to see whether this is right or not, right? This one, the equation here, or if you take your output as charge, then in this equation you can put. And time invariant because the coefficients are constant. The coefficients R, L, and C don't change with time, and that makes the system time invariant. So if you apply an input at some time and you get the response, just changing the time at which you're applying the input, right, will not change the response. The response will remain the same. This is a slightly loose definition of something being time invariant. But basically, if the system parameters are fixed, they don't change with time, and the system is called a time invariant system. Right? So in general, you will not write down an equation like this. The general equation can be written like this. So you have an nth differential of the output. The output was C, if you remember. Then you have these coefficients an minus 1, d n minus 1, ct divided by, so n minus 1 is the differential of the output, plus, so it will go on, and you have the first differential dct by dt. So this is a1, and in the last term is a0 ct is equal to, on the right hand side you have the inputs, and there are m terms for that, for example. So dm, the mth differential of the input, plus dm minus 1 dm minus 1 rt dm minus 1, and this is going all the way up to say b1 dRt by dt plus b0 rt. So this equation represents an ordinary differential equation with constant coefficients, right? In general, right? An ordinary differential equation with constant coefficients in general would be represented like this, right? So you can apply Laplace transformation to this equation and get it, in terms of the block diagram. You can write it down. So if you apply Laplace transform on the left hand side, and on the right hand side you have this is the nth differential of C. So you get C is the output. So you get Sn Cs plus An minus 1 Sn minus 1 Cs plus go up to A1 SCS plus A0 CS, and on the right hand side you get Bm S to the power n Rs plus Bm minus 1 Sm minus 1 Rs plus B1 Rs plus B0 B1 SRS plus B0 Rs. So if you want to write down CS by Rs, it will be Sn, sorry, it will be Bm Sm plus Bm minus 1 Sm minus 1 plus go on B1S plus B0 divided by S to the power n plus An minus 1 S to the power n minus 1 plus A1S plus A0. So this is the transfer function representation of this general differential equation. Okay? I can see, if you notice, there is no an term for this, right? There is no an term. So you could have, in this differential equation, why did you not have an here, right? When you had all these a's, because this is not required. You can always make, even if there is some coefficient right here, you can always make this leading coefficient 1 by dividing the whole equation by an, right? So if you have to write down an ordinary differential equation with constant coefficients of order n, you will be writing down something like this, without writing the an term, right? And why is it called? What is the order of this equation? If you remember again, order of the equation is the order of the basic variable which you're differentiating, right? And RT is the forcing function, right? And CT is the system variable. So RT is the input and CT is the system variable, which is the output in this case. So so basically the highest differential term corresponding to the differential of the output or differential of the system variable is called the order of the differential equation, right? In general, the order for real systems would always be higher here, so n would always be greater than m, right? So the order of the you can also say the order of the denominator polynomial is equal to the order of the differential equation or the order of the system, right? Okay, so this was about writing this in a more general way from the example. One more thing that I wanted to tell you was that you can actually from this equation where you wrote everything in terms of charge, you can for example have a different variable called output variable, right? So for example, the input variable for the original system that we drew was voltage, and the output variable is the capacitor voltage, right? So the input is this voltage and the output is capacitor voltage. Then how would the transfer function change? Now let me write down the differential equation again. The differential equation in terms of charge. What did we write? We wrote down Vt is equal to R dqt by dt plus L d square qt by dt square plus qt by c, right? And suppose we are interested in the voltage across the capacitor, right? Not the current through the circuit. So can we write down the transfer function as easily as we did for the current? The answer is yes. Now what you want to do is to put the differential equation in such a way that you have actually the the capacitor voltage coming in. So what you can do is a small substitution here. So we already know that Qt is equal to C VCT, right? The capacitor voltage, the charge is flow is going to be the same. So we already know this, that the relationship between the charge and the capacitor voltage is given like this. So we can write down, by substituting this back in this, we can write down Vt is equal to R, well, this will be Rc dVc t by dt plus, so if you differentiate, you have to put this CVC here, so you get LC d square. Now this is VC, right? D square VCT by dt square plus this QC QT by C is VCT. So you can take the Laplace transform on both sides and get Vs is equal to RC plus SRC, right? Plus S square LC plus 1, and you have this Vs, right? So VCS. So you can write VCS by Vs is equal to 1 upon RCS plus S square LC plus 1. And if you want to make the leading coefficient 1, sorry, this is not the leading coefficient 1, which we generally do, the highest degree term in the denominator has a coefficient 1, you can divide the numerator and denominator by LC. So you get 1 by LC S square plus R by LS plus 1 by LC. Right? So this is your VCS by VS. So you see, it's very simple to change the variable and still get the representation that we want to get. So to proceed further, I would suggest that all of us briefly revise what we have studied in mathematics about Laplace transformation, because we're going to use it again and again throughout the modeling part of this unit. And to briefly give you some of the general representations for some of the test inputs that we have seen on the last turn. So if your test input is impulse, right? Your test input is impulse, then the Laplace transform of the input is 1. If it is unit step, it is 1 by S. If it is unit ramp, it is 1 by S square. If it is some function of time, like parabolic or cubic polynomial, right? So it's t to the power n ut. Then it is n factorial divided by s to the power n plus 1. If it is a delayed, if it's an exponential term multiplied with ut, so you'll have 1 by s plus a. If it is a sinusoidal input, right, which starts at t is equal to 0, sine omega t ut. So it's a sinusoidal input that starts at t is equal to 0. When you multiply a pure sine with a unit step, you'll get something that will start at t is equal to 0, and normally your sine is going to be right like this. But if you multiply it with unit step, you will have 0 in the beginning, and then you suddenly have sinusoidal input starting from t is equal to 0. So the Laplace transform of that is going to be omega divided by s cap plus omega square. Similarly for cos. So these are some things that we have already studied before. So I will not spend much time on this. You'll also have to revise some of the basic properties of Laplace transform, the basic theorems of Laplace transform. So, for example, what is the definition, right? How is it a linear transformation? What happens if you shift the frequency by a? You're actually, or you're multiplying by an exponential term. So Laplace transform of e to the power minus at f of t is f of s plus a. Similarly, what happens if you shift time? So if you shift in time, you actually multiply with e to the power minus st in frequency. What about scaling? So if you scale, so Laplace transform of f of t is f of s, and Laplace transform of f of at is 1 by a f s by a. Similarly, for differentiation, integration, right? What are the Laplace transform theorems for all these, and what are the theorems for initial value and final value, right? So these are important theorems that you need to apply again and again, and these are all given in the book. So I hope you'll just revise some of this. Uh, uh, so this is the general transfer function that we were talking about, right? Uh, Now here in this case, the author has not made this leading coefficient 1, but we can always do that. Uh, that will, that is the general way in which we do it, right? So this is the governing equations for the capacitor, resistor, and inductor, and what are these equations in the S domain. So the capacitor governing equation as an integral is this. Differential equation is this, right? And this is the transfer function of the capacitor. If you take the output as the current, so if you write, so because what you have written here is v I t is equal to c dvt by dt into c. So if you write down the transfer function, you have is is equal to scvs. So if you write down the transfer function as vs by is, you get 1 by sc, right? So this is the impedance transfer function. And if you write down the transfer function as is by vs, right? If your input is current and output is if your output is current and input is voltage, then you have sc as the transfer function. So these are impedances, right? These are transfer function impedances, and these are transfer function admittances, right? So this is V. We normally represent the impedance by Z and the admittance by Y, right? Okay. So this is also something that you already know to some extent, and it is not difficult because you already know the governing equations, so you can easily write down the Laplace transformation of the governing equation, and then depending upon what is your input or what is your output, you either get the impedance as the transfer function or the admittance as the transfer function, right? Okay, so this is the RLC network, and this is the equation that we have found out, where the input is the voltage that we apply, and the output is the capacitor voltage that we get, right? Okay, so that's all for today. We'll be continuing with this in the next lecture. Thank you very much.